Okay, we're back. Remember, we're trying to find the, I'm going to type this up. We're trying to find a way to measure spread from the mean. The mean is 74, and we want to know how far up and down these values are from that mean. Okay, so we found the deviations, which seemed like a great idea because that measures how far everybody is from the mean. But the problem is that you can't add them up and divide by 10 or whatever this is, because when you add them up, they will always add up to 0 every time because of the nature of the mean. So what I'm going to do to make things turn positive on us is I'm going to square them. Now you can also do absolute value, and that leads to a different type of deviation called the absolute deviation, but that's not something we're going to work with in our book. So what I did was I took cell G2, which is that negative 14, and I put caret 2. Caret is above your 6. You have to do shift 6, 2, and that squares it. I'm going to go back up in that cell, make the handle, and fill it down the column, and there you go. There are all the deviations. Now I can add these up. I'm going to sum them. And if I sum them, I get 1790. Okay, now if you go back and look at the formula for variance, we've actually done quite a bit of it. We found the deviations. We found them squared, which is right here. Difference from mean, square it. Difference from mean, square it. Difference from mean, square it. And then you add them all up. And then you're going to divide by how many there were, capital N. So I'm going to do that right here. So there were 10 points. You can tell down here it says count was 10 right there. So I highlighted 10 rows. So I'm going to take equals that sum and divide it by 10. Actually, here's a trick. You can actually do the value count. Here. Hold on. Just so you know, N is equal to count of these cells. You can pick any of the columns, honestly, it doesn't matter. And it'll tell you there were 10. Okay, so when you want the variance, you can say, okay, equals that value, 1790, divided by that number, 10. There you go. This is called the population variance. And it has a symbol. Let me go see if I can find it. There it is. So it's sigma squared. That is your population variance. Congratulations. All right, now we got a couple issues, because even though that's the population variance, it's not like we actually found it from a population. Sorry, I've got to go back here. I'm looking for what I'm doing. There we are. Okay, so that was for population variance, but you only use population variance if you have a population. We don't really have a population. I mean, this was 10 data points from a test, right? But, I mean, how many math classes you've been in when there's only 10 students? And even if there were only 10 students in the class, it's a sample of a much larger group of all the people taking algebra tests, right? Right. So we actually want the sample variance. Now, the sample variance is the same thing. You take the difference and you square them, take the difference and you square them, and you add them all up. But instead of dividing by n, you divide by the degrees of freedom, which is n minus 1. Why n minus 1, you ask? Well, there's actually some very good reasons for it, but I don't want to get into it too much. So just suffice it to say that what's happening is you're working with a sample, not with a population. And that inherently means that you have a weaker understanding of what's going on. So to make fractions like this, because this is a fraction because you're dividing, to make them a little bit more large to accommodate for the wiggle room that we're going to need, you say, okay, I want to make my denominator smaller. Well, how much smaller? Well, just a little bit. So you make it 1 smaller. So instead of dividing by G14, i.e. 10, I do G14 minus 1 in parentheses, which makes it 9. You could just type 9 as well. And that makes sample variance. It's a little bit larger than population variance, because population variance can be small, because if this was a population, then you'd know everything there was to know about it. But in reality, it's only a sample. We don't know what the whole population's like. So we want to allow ourselves a bit more wiggle, right? A little bit more slop factor, right? And that's how we do this. So we make the denominator smaller. It makes the fraction a little bit larger, and it allows for a little bit more wiggle. Now, the population standard deviation, which the symbol for that is sigma, okay, that is equal to the square root, SQRT, of that number. There we go. And the sample standard deviation, hold on, is equal to the square root of the other number, the variance.